Okay, good afternoon, everyone, or good morning. Welcome to the new series, to the new events of the Hypatia Colloquium series at ESO. Just to remind you, this is a series dedicated to early career scientists, and we are very, very happy to allow and to hear all these exciting science that is done by the young PhD on or early postdoc students and actually astronomers at around us. So we are very, very proud and happy to welcome every speakers, and also we welcome also all the attendees. Thank you for being with us. Let me just very briefly remind that people can make questions after the talks that are half an hour. Basically, every speaker has half an hour slot with a 20 to 25 minutes talks, plus, followed by questions. You can make questions if you are following on the Zoom meeting via Zoom. Basically, you can make questions yourself, raising your hand, and then the chair will give you the word. Otherwise, you can, if you are following the event on YouTube, then just simply send your comment or question, post it on YouTube chat, and so that the chair will see it, and then the question can be passed to the speakers. If you do not want to leave the comment on the YouTube chat, there is still a third possibility, which is to use a form, a web form, and I left a link to the form on the chat, so you can click on the form, and then you can go and you can make a question, send it, and we will give it to the speaker. With this, so please be reminded also that there is a program online. You can go, and in the program you can see all the speakers, the entire series, and also you can click on the titles and look at the PDF where there is included not only the talk and the abstract of the talk, but also the curriculum vitae of our excellent speakers, so you can see them, you can know them, so then you can contact them. So there is a lot of material online, including also links to the previous talks, so you can always go and watch them. They will stay on YouTube. With this, I would like to also thanks a lot Marianne Heida. She is a ESO fellow, and she is gonna chair the session of today. And really, really thank you very much. Marianne is a super expert of massive star, binaries, stellar evolution. So she will for sure make the entire event even more nice than always, as always. And so let me thank again Marianne as a ESO fellow, but all our fellows and students who are at ESO, who are helping with the series in chairing, and this is great for us. So thank you. And Marianne, with this, hi, nice to see you. Please go ahead, and thank you very much again.
Yes, thanks, Giacomo. And welcome everyone to today's Hypatia Colloquium. Our first speaker today is Bachar Wehbe. Bachar did his master's and bachelor in Lebanon, and then moved to Portugal for his PhD, which he's doing now at the University of Porto. He's in fact defending tomorrow, so we're all wishing you very good luck. And he'll probably stay in Porto afterwards to work on ELT high-res instrument. And today he will talk to us about the atmospheric dispersion corrector and how he's actually building and commissioning that. So we're looking forward to hear from you, Bachar. I will stop screen sharing and then you can take over.
All right. Thank you, Marianne and Giacomo. So hello, everyone. My name is Bachar Wehbe, and as Marianne said, I'm a PhD student at the University of Porto and the Institute of Astrophysics and Space Sciences in Portugal. And as she said as well, tomorrow I will be defending my thesis, so wish me good luck. So let's talk about what I will be talking about today, and I will present to you briefly what I have been working on for the last few years. So atmospheric dispersion corrector from design phase to on-sky commissioning. So I always like to start my presentation with this figure because I think it summarizes all the work that I have been involved on. So as you know, the atmosphere can be represented by a prism. So when a white light goes through the atmosphere, it suffers from refraction. And in order to correct that effect, you need to find a way to regroup the dispersed light again into white light. And to do so, you can simply introduce another prism that is similar to the first one that represents the atmosphere, but in opposite direction to correct for that effect. And this is what we call the dark side of the atmosphere. And this is just playing on the words by using the Pink Floyd album, Dark Side of the Moon. So let's start. So as you know, the atmosphere is composed of different layers with index of refraction that is a function of wavelengths. So if you're observing a target at zenith, the light will go through the atmosphere without suffering any kind of dispersion or refraction. And what you see at the level of your detector is a nice white spot. Now, the further away you go from zenith, the more refraction the light will suffer in the atmosphere, and the different wavelengths will fall apart at the level of your detector. So instead of having a nice white spot, you will have an elongated spectrum. And this is what mainly the atmosphere is creating. So as I said, we can represent the atmosphere by a prism, and this is what we're showing here. And in order to regroup this light, Newton found out in 1671 that in order to regroup the dispersed light of a prism, you can simply introduce another prism to correct for that effect. And this is what we call an atmospheric dispersion corrector. So the idea is not new, it's actually very old and dates back to 1671. So as I show you here again, so the first prism is what we call the atmosphere, and the second prism is an atmospheric dispersion corrector, or in short, an ADC. And the idea is just to simply regroup the light. So an ADC, how does an ADC work? So an ADC works, or at least let's say that there are different types of ADCs, and one of the most common ones used now in high resolution astronomical instruments is what we call a rotating ADC. And the rotating ADC is in fact a set of two prisms that can either rotate together or do counter rotation. So the idea of using an ADC, so if you're pointing at zenith, the atmosphere will not create any kind of dispersion. You need to set your ADC to 0 in order to keep the result as a white spot. Now, the further away you go from zenith, you have more dispersion. You need to change the position of your ADC in order to introducing an equal amount of dispersion to that of the sky in opposite direction in order to correct it to keep your results as a white spot on the detector. So the question that I will try to answer during this presentation today are the following. So how can we model or design an ADC? How can we define ADC residuals requirement? And finally, how can we validate an ADC on sky? And by answering these questions, I will be able to close the loop in the life of an ADC from design to on-sky commissioning. So let's start. What is an ADC and how do we design it? So as I said before, the most common type of ADCs in high-resolution astronomical instruments is what we call a rotating ADC. And the rotating ADC is, as you can see here, is a set of at least two prisms, and each prism is in fact a set of two different classes that they can perform two different types of direction. So the first one, if the two prisms rotate together, as we see in the upper panel here, this will define the dispersion direction of the ADC. While if the two prisms counter-rotate, as we show on the bottom part of the figure, this will define the dispersion amount created by the ADC. So in order to correct for the sky dispersion, what you need to do is that you need to align the dispersion direction with that of the sky, in an opposite direction, of course. And you need to set the ADC to produce an equal amount of dispersion to that of the sky. So what is the problem? So the problem is that the design of an ADC is usually based on atmospheric models that, up to our knowledge, are not properly characterized. So in order to solve that issue, you need to introduce an ADC, and you need to create an ADC dispersion that will mimic the sky model by using set of classes. And the results are what we call correction residuals. And this is the difference between the sky dispersion minus the ADC dispersion. And these residuals are supposed to satisfy the requirements. I will get back to that by how we define the requirements. So how can we model or design an ADC? So as I said, the design of an ADC is based on atmospheric models that, up to our knowledge, were never tested before, at least not in the blue part of the spectrum. And this is when we go towards 400 nanometer or even lower. So we came up with a method that is based on measuring the PSF centroid as a function of wavelengths. I will go a bit more into details. And we submitted a proposal to UVIS and got accepted in the period 103. And the idea is to use a slit spectrograph, and by orienting the slit of UVIS along the atmospheric dispersion direction, and by removing the ADC from the optical bath, we will have observations directly affected by atmospheric dispersion. So how can we extract it? So we start by the upper figure here. And here what we show, it might be not very clear, but actually what we are doing is we are overlapping the science frame with the flat frame. And if we apply a vertical cut along the orders, you see here in the blue are the science frame and in the green are the flat frame representing the slits, and they overlap quite nicely. Now, if we zoom in on one of the orders, we can see that if we fit the science frame by a Gaussian and the flat frame by a double sigmoid, we will be able to extract from the fit the centroid of the Gaussian with respect to the slit. So we're using the slit as our reference. Now, if we repeat this procedure for a different cut, which means a different wavelengths, you can clearly see that these two wavelengths don't overlap on top of each other. In fact, they are apart. And the separation between these two wavelengths is a direct measurement of atmospheric dispersion on sky. So we need to repeat this step along all the wavelengths and all the orders in order to have a direct measurement of sky dispersion. Now, as you know, with every measurement comes uncertainty, and we were able to identify in our method 3 different main sources of uncertainty. The first one is the pixel scale, because the pixel scale is varying between what is listed on the manual, and especially along the y-axis, that's not very important for science observations, and what is happening in reality due to optical distortion or due to some misalignment. So we managed to recompute the pixel scale, and we found that it contributes to our final uncertainty by 0.9 milliarc second. Instrumental dispersion, and by instrumental dispersion, we mean that the actual optics of UVIS, and in particular the derotator of UVIS, are introducing an extra dispersion that we need to take into account, and that was at the level of 8.3 milliarc second. And finally, the standard deviation of the measurement themselves. So in total, we had an uncertainty of our method of 18 milliarc second for a dispersion in the blue at the level of 1,500 milliarc second, and that's quite amazing. At least for what we know, this was the first attempt to be able to measure the dispersion with such an accuracy. So if we repeat this step, as I said, for all the wavelengths, what we get is a direct measurement. So this is what we show here in the blue points. Now, in order to compare this atmospheric dispersion to the model, what we use is that we overplot the data by a model by using as inputs to the model the same atmospheric conditions at the time of observations. And these are mainly the temperature, the pressure, the relative humidity, and the zenithal angle. Now, what we call the residuals is the difference between the data minus the model. And here we show the residuals of different atmospheric dispersion models. So from a first approximation, you can see that the models are close to 0, and they are stable along the wavelengths range. Now, in order to do a proper characterization of the different models, we need to repeat this step for different bands, and using UVIS, we were able to measure the atmospheric dispersion from 315 nanometer to 665 nanometer. We repeated using different models, and the models we were interested in are the Bonch and Potocki, the Filippenko, the ZMAX model, and the ZMAX updated by Paolo Spanu. And we need to repeat the same step for different targets that cover different zenithal range of observations, hence different amount of atmospheric dispersion. And finally, we repeated each measurements 19 times in order to reach an accuracy at the level of 1%. This is equal to the 18 milliarc second for 1,500 milliarc second dispersion. So what we end up here, what I show you here, it might be a bit confusing, but it's actually quite simple, and I will try to explain it. So here we show the residuals, which is the models minus the observations for the 3 bands of that we measured using UVIS, so the blue and the 2 red bands of UVIS. And then for all the models, so each column is a different model, and for the 3 targets that we, for the 4 targets that we observed. So from a first approximation, you can clearly see that the residuals of all the models along all the bands and all the targets, they fall between these 2 dashed lines, which represent the uncertainty of our models. So first, we can see that the models are behaving okay, and all the models seems to be quite nice. Now, if we zoom or if we get close to the blue, we can clearly see that in the blue part of the spectrum, the ZMAX model is not behaving as good as the other models. And by now, it is well known that the ZMAX model is actually underestimating the atmospheric dispersion, and in particular in the blue. So what we can conclude is that when you are targeting or when you're trying to design an ADC with the residuals at the level of 50 milliarc second, try to avoid the Zemax model, especially when you go to as blue as 380 nanometer. So we know the models. Now we need to define the residuals requirements on the ADC in order to design such an ADC. So as you know, in order to understand the effect, the instrumental effects on science observations, we go from top-level scientific requirements to top-level instrumental requirements. And as far as I know, it used for the ADC residuals requirement, it used to be set by a scenario that we call by excess. So the residuals were always set on the safe side in order not to create problems. But that will increase the complexities in designing an ADC. So what we try to do is we try to connect the residuals requirement to effect on science observation from more a realistic scenario. So if you're observing at zenith, you have no observation. And if you think as the red circle as the diameter of your fiber, where you inject the light into the spectrograph or any kind of instruments, all the light will fall into the fiber. Now, if you have high dispersion or uncorrected dispersion, you start losing parts of the light. So the first impact of atmospheric or uncorrected atmospheric dispersion is flux losses. Now, this flux losses will actually affect your spectra at the level of a spectrograph, and it will create a change in the slope of the continuum of your spectra. So here is when you have proper correction of the dispersion, and here when you start increasing the amount of uncorrected dispersion, and you can clearly see how we start changing the slope. That will affect the weights of the spectral lines used in the pipeline to compute the final radial velocity. So the second impact is an impact on radial velocity. So to simulate these effects, what we did is that we started by simulating the amount of light that will enter the fiber at different zenithal angles, hence a different amount of atmospheric dispersion. So we know at each angle how much light is entering our fiber. Now, these curves are then multiplied by a template spectrum, and we use the tool developed by Martins et al. In 2018 in order to produce at the end spectra that are compatible with the HARP spectrograph, so we can feed the pipeline of HARPs in order to compute the final radial velocity. Now, another impact that we try to also understand is the impact of using different technical CCTs that are usually used to do the guiding and to inject the light into the fiber. And as you know, the guiding of a fiber, of a camera, is highly related to what kind of CCDs you're using. And this is mainly because different CCDs has different quantum efficiencies. And as you can see here, we have two different CCDs with different quantum efficiencies. So one camera will actually center the light at a shorter wavelength, while the other will center the light at a higher wavelength. And that will impact the way you are injecting the light into your fiber. So at the end, we will end up with a connection between residuals requirements in milliarc second and in function of radial velocity in meters per second and flux losses. And this is what we got. So what we know by now is that ADC residuals at the level of 100 milliarc second will barely affect your radial velocity. And this is the systematic errors. And this is in centimeters per second. So it's almost negligible. While the impact, and in particular in the blue, where we know that the dispersion is worse and the glass transmission is even worse, the flux losses in the blue are at the level of 1.5%. So what we need to bear in mind that when designing an ADC, we need to not only focus on the radial velocity errors, but also on the flux losses. So we started by estimating the models on sky. Now we know the residuals, so we can design our ADC. Now the last step is to validate such an ADC on sky. So as I said before, the ADC can perform two different types of rotation. The first one is when the two prisms are rotated together, and that will give you the direction of dispersion of the ADC and should be aligned by that of the sky, like here as the red vector, and the blue vector is the one of the total ADC. Or if you do counter rotation of the two prisms, that will define the amount of dispersion created by an ADC, and that should also be equal to that of the sky. So we need to find a way to validate these two angles on sky. And to do that, we will need to think of a way to quantify the correction in terms of amount and direction. And we found out that if we use the guiding camera images and we apply intensity contour plots to them, we can actually fit these contour plots by an ellipse. And by using the axis ratio A over B of an ellipse, we will be able to identify if we have a proper correction or no. So to explain how, we had three different images from the commissioning of Espresso, The first one here is when the ADC was supposedly working properly and we have a proper correction of atmospheric dispersion. The second one here is when the ADC was set to 0, so we are not correcting anything and your spot is affected by atmospheric dispersion, and we can clearly see how it starts to be elongated. And the third one is we over-exaggerated the position of the ADC in a way to increase the amount of dispersion. So we are doubling the atmospheric dispersion impact actually, and you see that the elongation is becoming much worse. Now, if we apply intensity contour plots to these three images, as we see here on the lower part, only from a visualization point of view, you can see that when you have a correction, you have a circle, and when you increase the amount of uncorrected dispersion, your circle starts to become an ellipse. Now, if you fit these contour plots with an ellipse, and you try to extract the A over B ratio, we can clearly see that the A over B ratio when you have correction is very close to 1, and it starts to increase with the increased amount of uncorrected dispersion. So by that, we were able to verify that at least our ellipse fit method works. Now, we need to use this ellipse fit method in order to be able to align the ADC, and especially these two rotations of the ADC with that of the sky. So to do so, we proposed a concept that I will try to briefly explain it here. So the alpha rotation is when the two prisms are rotating together. And this will define, as I said, the ADC dispersion direction and needs to be aligned with that of the sky. So if you look here, and if we can represent the ADC by a vector as well as the sky by a vector. So if the total ADC direction is perfectly aligned with that of the sky direction, your resultant will be 0 because they will cancel each other. Now, if you start rotating your total ADC, and this is the two prisms together by 90 degrees or by whatever step you want, you can clearly see that the residuals, the resulting dispersion starts to increase and to change direction. So that's for the alpha. Now, for the beta is when you rotate the two prisms, when you do counter rotation of the two prisms, and here we show the vectors of the two prisms. The more you open the two prisms, the more you increase the angle, the less dispersion the ADC will create, and that you will create more residual dispersion. So sky minus total ADC will start to increase as we show here in these vectors. So the idea is to do the following. You observe a target, you set your ADCs at total dispersion, and you rotate the two prisms together, and you do the same by counter-rotating the prisms by observing different targets at different zenithal angles. So why different zenithal angles? Because we started by simulating, let's say, different zenithal angles, and you can see here, this is the resulting dispersion. So ADC minus sky, or sky minus ADC. And what we need to do is you need to locate the 0 point where the dispersion is actually equal to 0. And this is where your ADC is aligned with the sky in terms of direction and in terms of amount. And it's easier to detect the 0 the more sharp your curve is. So when you're trying to align your ADC by doing an alpha rotation, you need to observe a target at a high zenithal angle, and this is the red, and this is where it's sharpest. And for the beta, you need to go to as low zenithal, as close to zenith as possible in order to detect the 0. So what do you end up with? So what we start with is you observe a target, you rotate your ADC as a full rotation in terms of alpha and beta. You have the final spots, you do the ellipse fit the intensity contour plots, and you plot the A over B ratio in terms of ADC rotation angle. The minimum A over B ratio, which should be equal to 1, is when you have a perfect alignment and perfect correction. And once you have these curves, you can locate your minimum, and your minimum will identify where your ADC is perfectly aligned. So in this method, we are able to align an ADC using on-sky observations, and you don't need to worry about any kind of extra dispersion you have on your system or any kind of field rotation you have in your system because you're relying on the actual observation. So to conclude, so we started by setting 3 questions at the beginning of the presentation. So how can we model or design an ADC? And we know by now that all the models tested are okay for residuals at the level of 20 milliarc-second, except for the Zmax that needs to be avoided in the blue. How do we define ADC residuals requirements? So we need to think about not only the impact of residuals requirement on radial velocity, but also on flux losses. And we know by now that residuals at the level of 100 milliarc seconds should be enough. And last but not least, how can we validate an ADC on sky? And this is by doing the alpha and beta scans in order to detect the minimum of the A/B ratio. Now, the last part was a concept that was supposed to be applied on NIRPs, but unfortunately, the NIRPs commissioning are still delayed due to COVID. And by that, I finish, and thank you.
Thank you very much, Bachar. That was a very nice talk.
Thank you.
Especially as an observer. I mean, I never think about ADCs, right? I just assume that they're doing whatever they're supposed to do. So that was enlightening. Are there any questions either here on Zoom? You can raise your hand or type in the chat, or you can type something in the chat on YouTube. While people are thinking, I actually do have a question. So you talked about validating the sky models, right? Of the of atmospheric dispersion.
Yes.
Is that generally valid what you found, or is that specific for Paranal in this case? Like, does it depend on the altitude of the observatory, or maybe local sky pollution or stuff like that?
Okay, that's actually a very good question. So we were lucky that our observations were done on the random days. So they were not done on the same day. So that's one. So we had different temperature ranges, different pressure ranges, and different relative humidity changes. The fact of being only for Paranal, so when you go from one location or from one observatory to another, you will change the altitude and the amount of dispersion will change, but the models are taking that into consideration. So since we observe different targets at different zenithal angles, we try to cover as much as possible the widest range of atmospheric dispersion. So we believe that this is valid for any observatory and any time of observation, let's say. So they are not specific to Paranal or to the day that we observe.
Okay, thanks. I see Dietrich has a question. Dietrich, you can unmute yourself.
Yeah, this was a remarkably clear presentation. Very good.
Thank you.
I have a question concerning the verification that you did by means of the acquisition camera. And there you are subject to the chromatic response of the camera. Have you considered instead to use, say, UVIS and remove the cross disperser and analyze the width and the curvature of the spectrum that you get in UVIS?
We didn't
because
think
there you
about
measure exactly the properties of the instrument. Huh?
Yes, yes. To be honest, we didn't think about it. We were more focused on fiber-fed, let's say, spectrograph, because it's true that it's a function of the camera itself, but we believe that once you align the ADC with respect to that camera, you should be fine because you're not changing cameras from time to time. It's always the same camera you're using. Now, what you're saying is can be valid, but I'm not sure at what kind of level of accuracy we will be able to reach. So just to give you a brief example, the method that we used, I didn't show the results here, but we used it to validate something on Espresso, and we were able to detect a change of 70 milliarc second, which is extremely small to usually detect. I mean, such levels of variations in principle don't affect the science observation, so it's not easily, you don't find the error in science, but it's not easy to detect at the level of the camera. And I would say that maybe if you go to the level of the spectrograph itself, it might be a bit harder to reach such an accuracy. That's why
on the other hand, if you don't see an effect with the equipment that you want to use, the effect is not important.
Yes, that's
so you
true.
You reach the sensitivity that you need with a given piece of equipment.
Yes, that's true. That's true. So, I mean, we know that because what we try to do is we try to rely on the sky instead of relying on just the geometrical optics of the instruments and what we know from the equations. Right? And when you go to such low levels of accuracies, it becomes more difficult. But we found out that this ellipse fit method, especially if you use the A/B ratio, it's quite sensitive to small changes. That's why we were convinced that this is a good approach to align an ADC on sky. but maybe we can discuss more later on your idea, and we can see if we can actually use UVIS more or such an instrument to validate it. But then you need to think that the majority of the new instruments are now becoming fiber fed. So you need to think also of an instrument that's fiber fed, not slit fed, right?
Thank you.
Thank you.
Are there any other questions here on Zoom, or I don't see anything on YouTube? Giacomo, we didn't get anything over email, did we?
No, not over email.
Okay, then I would like to thank Bachar again very much for your talk, and all the best tomorrow with your defense.
Thank you.
Our second speaker today is Giulia Santucci, and she did her master's in astrophysics at the University of Bologna, and then moved to Australia to do her PhD at the University of New South Wales in Sydney. So she's joining us, I'm not sure what time it is now, but it's rather late in the evening. So thank you, Giulia, for giving this talk at a rather inconvenient time. She'll be finishing her PhD next year, so we'll be looking for a job at some point. And she will tell us today about the stellar population gradients of SAMI central galaxies. And Giulia, you can start screen sharing and take it away.
Thank you. I'll start sharing. Can you see the screen?
Yes.
Great. Okay. Just let me.
Yes, it's
okay. Perfect. Thank you. So hi everyone. As Marianne said, my name is Giulia. I'm a PhD student at the University of New South Wales, and I'm going to finish very soon, in about 8 months. And yes, it's a bit late here. It's 11:30 p.m. So please be nice to me. Anyway, thank you for the great introduction and for giving me the chance to present my work here today. I'd like to talk about the stellar population gradients, such as metallicity, age, and alpha elements of SAMI central galaxies. This is the first project that I've worked on during my PhD, and I've done this working with my supervisor, Sarah Braff, Mireia Montes, and the SAMI team. I'll talk about SAMI a little bit later, but yeah, before we start, I'd like to give you a little bit of a background to explain what I mean with central galaxies and stellar population gradients. So to start, as you probably know, galaxies are usually found together, grouped together with other galaxies, and depending on the size of this collection of galaxies, we call them groups or clusters. We have a cluster of galaxies when thousands of galaxies are grouped together by gravity, and here is an example. But what I'm interested in is not the cluster itself, but the brightest galaxy in the cluster. And they're called, of course, brightest cluster galaxies, or BCGs. So these BCGs are also usually elliptical and located in the center of the cluster. This is also the reason why we call them central galaxies. In a group environment, instead of having a BCG, we have a BGG, so brightest group galaxy. To make things more uniform, here we will refer to this type of galaxies, calling them central galaxies in general. So they're both the brightest group galaxies and the brightest cluster galaxies. So from observations, we know that these galaxies are usually very massive, and they're also quite old and mostly passive. Also, due to their privileged position in the potential well, they are likely to have a high number of mergers in their life. So what we like to understand is how exactly do these galaxies form and how do they evolve? How important are the galaxies' interactions in their evolution? And what is the role of environment? So what does it mean for them to be a central galaxy or a satellite galaxy? So one of the other galaxies in the group or cluster. Doesn't make any difference. Well, we'll find out. So our current understanding of galaxy formation suggests that galaxies form in a two-phase process. during the first phase, we have called in situ phase, and that happens before redshift 2, galaxies become more massive by forming stars in situ in the inner regions. After redshift 2-3, the outer regions start to assemble by accreting ex situ stars, so stars that were formed in external galaxies through mergers with satellite galaxies, making up to 50% of the entire galaxy's mass. Now, evidence of this formation scenario are predicted to be preserved in the 2D kinematics and the stellar population radial profiles of present-day galaxies. For this project in particular, I've been focusing on the stellar population radial profiles of present-day galaxies. So you can see here in this picture an example of a metallicity radial profile for a galaxy. And we call the gradient the line that has been derived as the slope of the linear best fit of the data points. And the gradient tells us how the metallicity, or the age, in case of an age radial profile, changes going from the center of the galaxy to the outskirts. So studying how stellar population parameters such as age, metallicity, and alpha elements vary with the radius can give us information about the accretion history of the galaxy. So for example, the initial metallicity gradient is set by an initial starburst, with the metallicity decreasing going outward in the galaxy. But if the galaxy experiences mergers, then the gradient can change. Depending on the type of the mergers that they experience, they can have a shallower gradient or a steeper gradient due to stars being added in the galaxy's outskirt, or with a major merger due to the stars, the galaxy being completely disrupted. So we expect, according to simulation, we expect galaxies that had a high number of mergers, in particular also major mergers, to show shallower metallicity gradients. So for example, we would have points here instead of down here. Now, why is it so important for us to use the gradients and for central galaxies? Well, as I said before, central galaxies are predicted to have a larger number of mergers in their life due to their privileged position in the potential well. And so they're expected to have a less negative metallicity gradient. Hence, through the study of gradients, we can learn a lot about how galaxies, in particular central galaxies, are formed, how they evolve, and whether they have similar characteristics with the other galaxies, the satellites, in the cluster or group. So to do that, we use a sample of galaxies from the SAMI Galaxy Survey. And the SAMI Galaxy Survey is an optical integral field spectroscopy survey of low redshift galaxies. The interesting thing is that for SAMI, we don't have just one spectrum for each galaxy, but we have a 3D data cube, so that we have spatial information on 2 axes and spectral information on the z-axis, so that we can have one image for each wavelength and for each pixel a spectrum. So the data that I use is now public. So if you want to know a little bit more about it, you can have a look at CRUM 2021. The galaxies, the observations are free to download. So please have a look, play with them. They're really great. But yeah, so for our sample, we had an initial sample of about 3,000 galaxies with stellar masses spanning from 10 to the 8-ish to almost 10 to the 12 solar masses in the local universe. And the galaxies in our sample are located in different environments, spanning from isolated galaxies to groups and clusters. And they were divided into central and satellite galaxies. But the most important thing was that we had annular stellar population measurements of age, metallicity, and alpha element abundances up to about 3 Re, with Re being the effective radius, so the radius within which we have half of the light coming from the galaxy. And these measurements were taken by Scott 2018, and they were made in 4 apertures. So we had 4 different annular apertures. The spaxel in each aperture were summed, and the resulting spectrum was analyzed in order to extract the stellar population measurements using Lick indices that were then converted into singular stellar population equivalent age, metallicity, and alpha abundances through comparison with stellar population models. Now, once we selected the initial sample, we then used 3 main criteria to select the galaxies in our final sample. First of all, we selected passive galaxies following the spectroscopic classification of OWERS 2019, so that only passive galaxies were included in our sample in order to ensure a like-to-like comparison between central and satellite galaxies. We then selected all the galaxies that had mass above 10 to the 9.5 solar masses due to the low completeness of galaxies at lower masses. And then we also selected galaxies that had at least 3 measurements, so 3 annular measurements between 0.1 Ari and 1 Ari, as well as galaxy with measurements beyond 1 Ari, but at least 1 within 1 Ari, in order to probe similar spatial regions for our sample of galaxies. However, we have an additional criteria that we had to add for the alpha elements. We also required the signal to noise of the spectra to be greater than 20 in order to account for the greater uncertainties associated with measuring this parameter. That said, you can see here the black crosses are all the galaxies in the SAMI initial sample. Then we have passive galaxies as green crosses and the galaxies in our final sample as red crosses. So our final sample consisted of 533 passive galaxies selected with reliable measurements for metallicity and age. Of these, just 332 had reliable measurements for alpha elements. And then when selecting central and satellite galaxies, we had 96 central galaxies and 437 satellite galaxies. Again, 79 centrals and 253 satellites with alpha, reliable alpha measurements. Now, if we have a look at how central galaxies look, a radial profile for central galaxies, satellite galaxies, you can see here 2 examples for metallicity gradients. So the central galaxy is the one in purple on the top panel, while we have a satellite in blue in the lower panel. As I said before, mergers can remix the metallicity in the galaxy so that the metallicity gradient will appear less negative for galaxies that had undergone more mergers, while compared to the ones with less mergers or different type of mergers also. So in this work, we derived the gradient for each galaxy by applying a log-log linear fit to the stellar population measurements. And then, well, the fit that we performed also took into account the errors of the measurements. And then the fitted slope is taken as the galaxy gradient, and the uncertainty on the gradient is derived using a 1000 Monte Carlo realization. So perturbing each annular value inside its errors, and then using the standard deviation from the mean value of the slope as the uncertainty on the gradient derived. However, these are just 2 galaxies out of more than 500. So to see if there's actually a real difference between central and satellite galaxies, we need to have a look at the whole sample. So you can see here our final results. This is for metallicity gradients. We have central galaxies in purple in the panel on the left, and then we have satellite galaxies in blue middle panel, and the bold points are the median values for each mass bin, because we divide the galaxies in different mass bins. This was to better visualize whether there was an underlying trend. And then we plotted the mass bins together in the plot on the right in order to better visualize whether there's any difference between the gradients of central and satellite galaxies. So what we found was that the metallicity gradients for the galaxies in our sample are generally negative, and we do not see any significant difference between the gradients of central galaxies and satellite galaxies, as you can see here. However, we do see a slight trend of the gradients with stellar mass, so that although you can't really see it that much here, but there's evidence of a slight trend of the gradients with stellar mass, so that the gradients become less negative with increasing stellar mass. Although it's, as I said, it's not a very strong trend. Then, if we have a look at the age gradients, again, we have central galaxies in purple on the left, and then satellites in blue in the central panel, and the median values for each mass spin plotted together for both satellite and central in the right panel. So this time we find that galaxies in our sample usually have slightly positive age gradients, although there's a lot of scatter. And when we plot together central and satellite gradients, we do not see any difference between central and satellite galaxies, and we do not find any trend with stellar mass as well. Then looking at the alpha elements, again, central galaxies in purple, satellites blue, and the median mass spins plotted together on the left, on the right. We find that the alpha elements gradients are usually slightly positive or even close to zero. And again, we do not see any difference between central and satellite galaxies, but we do find a trend of the gradients with stellar mass, so that the gradients become closer to zero, so the values are lower with increasing stellar mass. So we also checked whether there was any trend with different halo structures. We divided the galaxies in our sample in different halo mass spins, and then we compared the galaxies in the low mass spins with the galaxies in the high mass spins, again divided by central and satellites. So you can see them here as galaxies in high mass halos as crosses. Then we have the blue ones, there are satellite galaxies, purple ones, central galaxies, and then the squares are the galaxies in low mass halos. Again, blue ones are satellite galaxies, pink central galaxies. We have metallicity gradients on the left, age gradients in the central panel, and alpha gradients on the right. So if we have a look at the metallicity gradients for galaxies in high mass halos, we can see that there's not much difference between central and satellite galaxies, especially if we look at galaxies in similar mass spins, like here. We do not see any trend with stellar mass. It's almost flat. However, when we have a look at how the gradients are for the galaxies in low mass halos, we see that again, if we look at similar mass spins, there is no difference between central and satellite galaxies. We cannot say much for galaxies at higher masses since they're all centrals. And but we do see a trend with stellar mass for these gradients, so that the gradients of galaxies with increasing stellar mass are less negative than those of galaxies of low stellar mass in low mass halos. However, for age gradients, they're generally the same for both central and satellite galaxies, with no trend with stellar mass regardless of the host halo mass. Same for the age gradients, there's no significant difference between central and satellite galaxies, and there's no difference with environment as well. So just to summarize, what we found in the galaxies in our sample was that the metallicity gradients are generally negative, and we have evidence of shallower gradients with increasing stellar mass, so that the gradients become less negative with increasing stellar mass. We find age gradients that are usually positive, although we do not find any trend with stellar mass. Alpha gradients are flat or slightly positive, and there's a negative correlation with stellar mass, so that the gradients become less, well, the value of the gradients are lower with increasing stellar mass. We do not see, however, any difference between stellar population gradients found for central galaxies and for satellite galaxies, nor for different halo masses. So these results point to a similar formation and evolution history for central and satellite galaxies, passive galaxies in our sample. However, even though at the beginning I said that we had measurements up to 3 RE, if we look at the central sample only, the majority of our galaxies do not go above 2 RE, so that we're only probing the inner region of these galaxies. So the only thing that we can actually say is that the inner regions of central and the satellite galaxies are similar. So they have evolved and formed in a similar fashion. But again, as I said at the beginning, this was just one of the possible way to explore the evolutionary history of these galaxies. The other one is looking at the 2D kinematics, and that is what I've been doing in these last few months. I've been applying spatial orbit superposition models to SAMI passive galaxies in order to retrieve, reconstruct the orbital structures and the internal mass distribution of these galaxies to better understand their merger histories and how they form and evolve. Now, if you're curious about this, I'm giving a seminar on the 22nd of July about this for the Astro 3D ECR astronomers in Australia seminar series. It's at 10 p.m. for Europe, I'm sorry, but it's a good time for America, apparently. But yeah, I'll leave you with this. Thank you again for listening.
Thank you very much, Giulia. That was a very nice talk. Does anybody have questions here on Zoom? You can raise your hand or in the chat on YouTube while people are thinking. So you said you sort of expect to see a difference, right, between the satellites and the central galaxies, but you don't really. Do you think, is that mainly because the theory is wrong or needs to be improved, or do you think it's mainly your observational biases because you're looking at the central bits?
I think it's for the central bits, because even in simulations, what we see is that the evidence of later accretion is more evident when we look at radii that are above 1.52 RE. So to really see those evidence of later accretion, you have to go wider. And so we need wider observations for sure. But the thing is, the SAMI observations are great, but they have a fixed field of view. And of course, my central galaxies are huge. And so we can't see more than that. It's just the inner region. But that's still interesting because at least it points to central galaxies, at least the inner regions of central and satellite galaxies being formed in the same way. So they agree with the two-phase formation scenario where the inner regions formed at the beginning. And that's why we have similar trends, at least.
Right. So the problem is really field of view and not so much sensitivity. I would have thought that that might have been.
Well, it might be partly because of that too, of course. But I think for us, at least for the central galaxies, might be because of the field of view, mostly, because we can't really see those outer regions, the outskirts of the galaxy. So we can't really say much about them.
Interesting. Okay, I see a raised hand from Boris, and then after that we have a question from YouTube. But Boris, please.
Yes. Hello. Thanks for the talk. Can you go back to your last slide before the conclusions?
This one. Sorry, before the conclusions.
No, before the conclusions. One more. Yeah. So in the leftmost plot here, you say there is a trend for the in the low mass halos. Right? If I look at your arrow bars, that trend is entirely consistent with no trend.
Yes, but we tested that.
So can you comment on that, and can you also comment how many galaxies you have in each bin? Because of course, if there's 5 galaxies in each bin, this is all noise. If you have 10,000, which you don't because it's SAMI, but then of course this is much more significant.
So there are, if I remember correctly, although all the details are in the paper if you need, there are something between 25 and 32 for each mass bin. The mass bins, yeah, actually I think 32 for each one of them. For the satellites, there might be about 20 for the centrals too. even probably less. Sorry, I can't remember the exact numbers, but they were definitely more than a couple, because that's why we did that. But so the trend that you see there, we did a candle statistic test for that to check there was actually a trend, and there is a trend within 2 sigma. Sorry, I can check it. I think it was within 2 sigma probability.
Okay.
Yeah.
Just
Again,
looking at the error bars, it's significant. It's consistent with 0 as well. Okay, thank you very much.
No worries.
So someone called Star Wars Meerkat is asking on YouTube a very basic question. If the high metallicity is indicative of older stellar populations, then what leads to the metallicity and stellar population age gradients being opposite signs?
So you mean, what do you mean opposite signs?
Well, I think you saw the, maybe you can go back to the plots with the, yes, these.
Yeah.
So you see that the metallicity gradient is negative, I think, right?
Yeah.
And
yeah, usually negative, because we have higher values of metallicity in the center of the galaxy and then lower going into the
but the age gradient is positive.
Yes, because we have, again, younger stars in the center, since we still have star formation. That's why we have higher metallicities as well. And then going to the outskirts, we find the older galaxies. There are also more, less metal rich.
Okay, so I think then the assumption in this question is not correct, because they assume high metallicity indicative of older stellar populations, where actually here the higher metallicity is connected to the younger stellar populations.
Yes.
Okay.
Within the galaxy, yeah.
Right. I think that probably answers the question. And then Laura Sanchez was asking in the Zoom chat, are you planning to extend the study to other data sets where you reach further away in effective radius?
I would love to. Yes, definitely. We have a few mute observations for this galaxy, for some of these galaxies, but of course, to reach farther away in the effective radius, you need a long time to observe the galaxy, especially these big galaxies. So we don't have a big sample for that, just 8 galaxies. If I'll have time after my PhD, maybe I'd love to do that. But there are so many things that I love to do that I don't know if I'll have time. But yes, they would be amazing to do.
Okay, thank you. Pavel Krupa has a question on Zoom.
Yes, hello. Thanks for the presentation. It's a really wonderful project and very clever to compare the satellites with the central galaxies. But from the data I've seen, it seems that, well, can you exclude a monolithic formation scenario for these early type galaxies?
So what we found, so the values of the gradients, comparing them with simulations, at least the median values are more close to the values that you get from a 2-phase formation scenario than a monolithic one, because the monolithic one had values that went from negative 0.5 to negative 1. And we do have some galaxies with those low values, but the general trend is not that negative. So that's why, and also for the alpha elements, so later accretions should bring values closer to 0, and the same is for age gradients, having positive values or more flatter gradients is due to later accretion. And so that's why, well, you can't completely rule it out probably, because we still have big error bars, but it points to be more in agreement with the two-phase formation scenario than the monolithic one.
So you discussed this in your paper, right? What you just said. Yeah. Okay. Good. Yeah. Okay. Thank you.
No worries.
Are there any more questions, either on Zoom or YouTube? I don't see anything. So thank you, Giulia, for this very nice talk and for answering the questions. And also thank you to Bachar again You both gave great talks. And I think, Giacomo, you will...
Yes, just to conclude. Yeah, we can conclude. Thank you. Perfectly in time, actually. So thank you, Marianne, for chairing the session. Thank you very much. And also thanks from my side to Bachar and Giulia. And congratulations. There are some congratulations on the chat. And also, Tom, good luck to Bachar in particular with your thesis tomorrow, with your defense. And good luck, Giulia, with your next future. Thank you everyone for attending the event. Let me remind that the next one will be next Tuesday, usual time at 3. And so see you next week. Thank you very much again. Ciao, Marianne. Ciao, everyone. Bye-bye.
Ciao.
Ciao.